Hello. We shall continue with Einstein's special theory of relativity in this lecture. So this is chapter 28 on special relativity. So in the last lecture video, I tried to give you an idea, excuse me, of the sort of difficulties that scientists had in the late 1800s when they tried to apply Newton's theory of mechanics to resolve certain problems. The predictions of the theory were completely inconsistent with the experimental observations, and therefore it was necessary for Einstein to develop this new set of ideas that could resolve the problems. And as I said, Einstein then essentially changed the whole notion of space and time. So we're going to discuss one more consequence of the two postulates today. Well, let's begin by reviewing the two postulates that form the basis of Einstein's special theory of relativity. And the postulate number one says that the laws of physics have the same form in all inertial frames. No inertial frame of reference is special. Okay, there is no absolute frame of reference. So we shall say that the laws of physics, they remain valid. Or you could say have the same form in all inertial frames of reference. So if you write any physics law, it will not be different just because of the way you're observing it. Physical quantities, as in velocity, momentum, kinetic energy, can be different, but the law of the law of conservation of energy will not change. The law of conservation of linear momentum or angular momentum will remain the same. 2, the constancy of the speed of light. The speed of light in vacuum is 3×10⁸ meters per second, period. In all inertial frames of reference. Just be complete in all inertial frames of reference. It does not depend on who's observing it. It does not depend on the motion of the source of light, whether the light source is moving towards you or away from you. You're going to measure the same speed regardless, 3×10⁸ meters per second, as long as you are in vacuum. Okay. And then based on these two postulates, Einstein derived a number of consequences, and we stated two of these in the last lecture. The first of these was the relativity of simultaneity. And this says that if two observers observe the same two events, they may not necessarily agree that the two events were simultaneous, occurred simultaneously, if there's relative motion between the two observers. So simultaneity is not absolute. It depends on who's observing it and from what reference frame. And the second consequence that we observed in the last lecture video, that's time dilation. here's the idea of time dilation. Suppose that there is an observer inside a spaceship that is moving at some speed v. This observer has a clock with which they can measure the intervals between events. And let's call this observer A. And let's say that there's an observer standing on Earth, it's called observer B, who can somehow see into the spaceship and time the intervals between the same two events that observer A is looking at. Well, in observer A's frame of reference, she writes that the interval between the two events is delta t naught. Observer B observes the same two events and measures the time interval to be delta t. Now, according to the old theory, according to classical physics, Newtonian physics, there's no difference between these two times. So according to Newton's theory, delta t and delta t naught are completely the same. But according to Einstein's special relativity, these two times are not the same. So according to the special theory of relativity, delta t is actually given by the following expression. Delta t is gamma times delta t naught. And you recall that gamma is 1 over the square root of 1 minus v squared over c squared. And this quantity here is greater than 1, except for the very non-interesting case where the velocity is 0. So gamma is greater than 1. Okay, which clearly means that delta t is greater than delta t naught. And we mentioned that delta t naught is called the proper time interval or simply proper time. And delta t, on account of the fact that it is expanded, is called the dilated time. So time is dilated from the point of view of observer B, who is observing the clock moving. So delta t naught we call proper time, and delta t we call dilated time. So this is the takeaway that you should have. This is what I want you to take away from this discussion. Moving clocks run slower because the time interval between one tick and the next tick is longer, it's dilated. Therefore, from the point of view of observer B, this clock moves slower. Moving clocks run slow. Okay? So that in general, this is the only time the time is a proper time interval, when the measurement is performed when the observer is at rest with the clock. In all inertial frames of reference, in all other inertial frames of reference, you will measure an expanded time interval. Okay, so, and I know that I stated this before, but let's, for the purpose of clarity, state these again. The proper time, delta t naught, this is the time measured by an observer who is at rest with a clock, essentially, or with the same two events occurring in the same location, at her location. It's at rest with the clock. Okay, and delta t here, this is the time interval that's measured from all other inertial frames. Okay. If this idea of time dilation seems strange to you, it is very likely because of the fact that everyday speeds are so much smaller than the speed of light, and therefore gamma is, to all intents and purposes, 1. And for that reason, we don't observe any difference between delta t and delta t naught. Let me very quickly demonstrate this. Let's consider a very fast car. So a Lamborghini that's traveling at 225 miles per hour is a good example. 225 miles per hour. You can show this is about the same as 100 meters per second. Better yet, let's even say somehow this car is able to move 3 times as fast. So let's use v of 300 meters per second. Then, when we calculate gamma, we have to do v over c is, so 300 divided by 3 10 to the 8. And so this here is 1 10 to the 6. So this is 1 divided by 1 10 to the 6, or this is essentially 10 to the negative 6. So that the v squared over c squared is 10 to the negative 12, which is a very small number, 0.00, 0.00. It goes on, it's a very, very tiny number. So by the time you subtract it from 1, find the square root and then divide that by 1, which is what gamma is, then you get a very, very small number, which is almost the same as 1. So to all intents and purposes, you do not observe any difference between proper time and any other time. Okay. So I want to do a quick example also to illustrate the point that time is dilated. So in the example that we did for observers A and B, let's consider the case where the spaceship is moving at some very high speed, 0.9 times the speed of light. Then, V over C, as you can see, if I divide both sides by C, I get 0.9, right? Which means that if I square both sides, V squared over C squared is then 0.9 squared, which is 0.81. So if I do 1 minus v squared over c squared, I get 1 minus 0.81, which is 0.19. Then if I do the square root of 1 minus v squared over c squared, I get the square root of 0.19. And finally, gamma is the reciprocal of this. So gamma becomes 1 over the square root of 1 minus v squared over c squared. And that should be 1 over the square root of 0.19. And if you do this calculation, you get a number that is something like 2.29. It goes on for some time, but 2.29 is fine. Now, this is to say that if the observer A measures a certain time interval, the proper time, and gets 1 nanosecond, then observer B measures a dilated time. So then delta t is gamma delta t naught, or 2.29 times 1 nanoseconds. Okay, so we do not all measure the same time intervals. Now, This is not some academic exercise in numbers. This is actually, turns out, how nature works. And the only reason we don't see it in everyday life is because the everyday speeds that we have are extremely small compared to the speed of light. The dilation of time has been proven many, many times over. And one very good example, so I'll just, before we do any problems, I'll just tell you about the evidence for time dilation. And the first of these has to do with a particle called a muon. Muons are particles that are like electrons. They have the same charge as an electron, but they are about 200 times as massive. The mass is 200 times, about 200 times than the mass of the electron. These particles are created in the upper atmosphere when cosmic ray particles collide with nuclei in the upper atmosphere. Turns out that this particle, when it is created, is unstable. It has a lifetime, after which it decays into an electron and two neutrinos. When the lifetime of this particle is measured, and we'll say more about this in a later chapter, I'll define the lifetimes properly. But when the lifetime is measured in the rest frame of the particle, we get about 2.2 microseconds. When these particles are created, they travel extremely fast. They travel at speeds that are approaching the speed of light, where v is about 0.998 times the speed of light. Okay, they're moving extremely fast. At the speed, you can easily calculate how far they can travel before they decay. Let's do that. Distance is speed times time. So this is how far they can travel before they decay. 0.998. C is 3 10 to the 8. And then the time is 2.2 10 to the negative 6. And we're not going to get a calculator because this number is essentially 1. So we get 3 times 2.2, which is 6.6. So this here is about 660 meters. This is how far the particle should travel before it decays. Turns out that this particle can actually be observed on the surface of Earth. The only way this is possible is if the particle had traveled way past 5,000 meters. Okay, the distance from the upper atmosphere to the surface of the Earth. At least 5,000 meters. How does this particle do it? Well, time dilation is the only explanation that resolves this problem. Okay? All right, number 2. I'll just give you a very simple example, and then we shall move on to do a few problems. Our global positioning systems, GPS systems that everybody uses every day, this consists of 30 or so satellites that are orbiting. I wish I had used a different color to describe the orbits, but these satellites are orbiting the Earth, and they orbit the Earth 2 times every day, about 30 of them, and there are local receivers, GPS receivers, that receive light signals that are transmitted from the satellites. And by a process of triangulation, it is then able to calculate your location. And we want to do so with an error of only about 10 meters. But these satellites, they move very fast. And they move at about 4,000 meters per second, which of course is still very much less than the speed of light. But it's fast enough to cause the clocks to go slow. Remember that moving clocks run slow. So in fact, this speed leads to a slowing of the clock by about 7 microseconds per day. Okay? And if you did not take this into account when you do the triangulation, then you're going to mess it up. You can do a very simple calculation because light travels at the speed of light, and so you can do 3 10 to the 8 times 7 microseconds, and you can see that this is very clearly greater than plus or minus 10, let's just say the 10 meters that we're trying to obtain. In fact, this is what, some 21 10 to the 2. Okay, so GPS takes time dilation into account before we get the accuracy that we can get today. In 1971, very precise cesium beam atomic clocks were initially synchronized. A few of them were synchronized, a few were left in the laboratory, and some were put on airplanes. The airplanes were then flown for a very long time, for the period of about 2 days, and then returned to the naval laboratories. And when the two clocks were compared, indeed, the clocks that had been in motion were running slow by an amount that was consistent with Einstein's predictions. So this is very true. And to say that time is dilated, clocks move slow, means all processes that involve time intervals will run slow. The heartbeat has time intervals. It's going to run slow. Biological processes, chemistry, in fact, everything that needs time intervals is going to run slow. So keep this in mind. Moving clocks run slow. Well, with this introduction then, we can do a couple of problems. So our initial problem, our first problem, is taken from the OpenStax book, page 1138. OpenStax textbook. And it says, this is question 3. Particles called pi mesons are produced by accelerated beams. By the way, before I finish this, one other evidence is that today we have huge particle accelerators that cost millions and millions of dollars. If time dilation were not taken into account in our observations, we would be completely off. Okay, but in fact, Einstein's theory gives us the correct results all the time. Okay, so to go back to this problem, now if these beams travel at 2.70 10 to the 8 meters per second and live 2.60 10 to the negative 8 seconds, that is to say their lifetime before they decay to other particles. So this is the lifetime when they are at rest. When at rest, relative to an observer. How long do they live as viewed in the laboratory? So, these particles are called pi mesons, and they are produced by accelerated beams. Now, these particles travel at 2.70 10 to the 8 meters per second. So our speed v is 2.70 10 to the 8 meters per second. And if you watch the first lecture video, 2.70 10 to the 8, this is 90% of the speed of light, because 2.7 divided by 3, that's 0.9. So we can write this as 0.9 times the speed of light. They live 2.60 10 to the negative 8 seconds when at rest relative to an observer. So this time here is the proper time interval, because this is the time measured when these particles are at rest with respect to the person performing the measurement. So our delta T naught is 2.60 10 to the negative 8 seconds. And the question is, how long do they live as viewed in the laboratory? Well, the question then is, what then is delta T? This is what we have to solve. Okay? And as you can see, the problems on special relativity will not be very hard. At least the algebra will not be very hard. The problem may be with recognizing what is proper time and what is dilated time. So our equation says that the dilated time is the same as gamma delta T naught. We have to first find gamma. We've done this before, but I'll go through the process. V is 0.9 times the speed of light. Now I know some of you would like at this stage to just plug the numbers in to your calculator directly. However, my suggestion is that take your time, do things carefully. Follow me. If V is the same as 0.9 times the speed of light, then if I divide both sides by C, then V over C is the same as 0.9. Oh, we did this a minute ago, which means that V squared over C squared is the same as 0.9 squared, which gives us 0.81. I think we just did this. All right, so this means that 1 minus V squared over C squared is the same as 1 minus 0.81, which is 0.19. And then you can find gamma as follows. So you take the square root and find the reciprocal. So this is 1 over the square root of 0.19. And as I said, check this. This is 2.9 something something. For Quest, make sure that you enter more numbers, so that there's no ambiguity. Let's do the 0.19, and we find the square root, and we find the reciprocal, and we get 2.294,157. So to be more complete, well, then clearly we can find delta T. Delta T is then 2.294,157 times the proper time was 2.60 10 to the negative 8 seconds. Which gives us 5.964809 10 to the negative 8 seconds, which is about 5.96 10 to the negative 8 seconds. Okay? All right, let's do another problem. And like I said, the difficulty here may not be the algebra. It may just be in recognizing which is the proper time and which is the dilated time. Once again, do this calculation of gamma carefully. Do not be in a rush. One potential problem is the following. See, when we wrote that V is 0.9 times the speed of light. Now, I've seen this happen before, that students then do V squared over C squared as follows: 0.9 squared divided by 3 10 to the 8 squared. Do you recognize the error here? V is not 0.9. V is 0.9 times the speed of light. So this is clearly incorrect, right? This is not 0.9, this is 0.9 times. If you do this, then you'll end up with gamma that's very close to 1. And then you'll be in error. So please do not do this. All right. Let's do a slightly different kind of problem. Okay. So that I can erase this. So this problem says a pi meson, so a neutral pi meson is a particle that can be created by accelerator beams. If one such particle lives 1.4 10 to the negative 16 as measured in the laboratory, if one such particle lives 1.40 10 to the negative 16 seconds as measured in the lab, and 0.84 10 to the negative 16 seconds when at rest relative to an observer. When at rest relative to an observer, what is its velocity relative to the laboratory? So, this particle, when it's created, has a lifetime of 1.4 10 to the negative 16 seconds as measured in the laboratory, and 0.840 10 to the negative 16 seconds when at rest relative to an observer. That should tell you that the 0.840 10 to the negative 16 seconds, that's proper time. Here's another way you can tell. Proper time, the proper time interval will always be the shorter of the two times. Proper time is the shortest of all other time intervals for the same two events. So in this case, the dilated time has been observed to be 1.40 10 to the negative 16 seconds. And the question is, what is the velocity? So this is v. The question then is, what is the velocity? V is what? Okay. Well, let's continue here. So clearly from our time dilation equation, delta t is gamma delta t naught. And we have 1.40 10 to the negative 16 is the same as gamma times 0.840 10 to the negative 16. Obviously, gamma is then 1.40 divided by 0.84. 10 to the negative 16, as you can see, canceled out. So let's do this calculation. So we have 1.40 divided by 0.84. And that gives us 1.666667. Okay. Gamma, you recall, is 1 over the square root of 1 minus v squared over c squared. So, my suggestion, the very first thing you should do, square both sides to get rid of the square root sign. So, we get next, this becomes 1 over 1 minus v squared over c squared, and that's the square of that 1.66666 squared. And that gives us 2.77777. It's very interesting. Then do the reciprocals. 1 minus v squared over c squared is then 1 over 2.77777, which gives us 0.36000. Okay. So the reason we did it like this is so that now we have the number 1 minus a fraction is that. So that means that, so let's continue here now. So that means v squared over c squared is 1 minus 0.36000. Okay. Which is 0.64000. At this stage, you can just find the square root of both sides. So v over c, the square root of 0.64 is 0.8. 0.8. Now you're done, because you can easily multiply both sides by the speed of light to get your v. So from here we get that v is 0.8 times the speed of light is 3.0010 to the 8 meters per second, and that gives us 2.4010 to the 8 meters per second. So once again, just take your time and do this carefully, and you will get the right answers. All right. I'm going to finish this discussion with one other consequence that Einstein derived. And not only are time intervals different depending on which inertial frame of reference the two events are being observed from, but the distance from one point to another point, what we would call a length, the length is also affected. The length is dependent on the observer that is performing the measurement. And that's called length contraction, the contraction of length. So this here is consequence number 3. We should call this length contraction. And let's use a very simple thought experiment, which Giancoli does very well. So we're going to use the example in Giancoli to do this. Suppose that we have an observer that's standing on planet Earth. This is Earth. There's a very far off planet, Neptune. And there's an observer that's inside a spaceship that's traveling at the speed v from Earth to Neptune. There is one observer that is earthbound. As you can see, from the point of view of the earthbound observer, they are stationary with respect to the Earth-Neptune system. Let's label these A and B, observers A and B. So from A's point of view, so observer A is at rest with respect to the Earth-Neptune system. For this reason, she writes that the length is not a proper length because she performed the measurement at rest. And distance is speed times time. Distance is speed v times a certain time interval. But let's do the same thing now from the point of view of observer B. Observer B. Well, from the point of view of observer B, so this is her in a spaceship. Consider this, you've had this experience before when you're sitting on a train and the train is pulling away from the train station. Very smooth, no vibrations, in other words, no acceleration, it's moving away. What you see is that you see the station moving away from you. You don't see yourself moving, you see the station moving away from you. And this is the perspective of observer B. So observer B will say, oh, Earth is departing from me with a speed v. Similarly, she sees Neptune approaching her with a speed v. She is at rest. She sees Earth pull away and she sees Neptune approaching her. So, the two events, departure and arrival, occur at the same location, at her location. She measures proper time. So, departure, oh, let's say, from her perspective, Earth departure and Neptune's arrival both occur at her location. She just sits and the two events occur. And for this reason, she writes the following equation. She writes length is v times the proper time interval. So let's call this equation 2 and let's call this equation 1. And now the speed v is the same in both cases, so we can easily show from equation 1 v is the same as L naught divided by delta t. And from equation 2, v is the same as L divided by delta t naught. We can rearrange this, and L naught over L is then delta t over delta t naught. But we know about time dilation. We know how delta t and delta t naught are related. And they are related through gamma. And we're done with the derivation. So from this, we see that L is the same as 1 over gamma times L naught. Now, since gamma is greater than 1, I keep saying this, for all velocities not equal to 0, gamma is greater than 1. That means 1 over gamma is a fraction, and therefore L is a fraction of the proper length. So 1 over gamma is a fraction And this means that L is less than L naught. And we say that the length is contracted. Okay? But length is contracted only in the line along which the motion occurs. Only along the direction of motion. If this is not clear to you, let me just give you a very brief summary. As follows. Consider, once again, a spaceship that is lying, let's say, in a warehouse. And here you are, and you have a meter stick. And you're going to perform a measurement of the length of this spaceship. Now let's put the spaceship on some support. Okay. What you measure, because you are at rest with respect to the spaceship, this here is L naught. You measure L naught. Now, if the same spaceship is launched and it's moving at some speed v, and you're on Earth measuring the length of this spaceship with your meter stick, you're not going to measure the proper length, because now you are in relative motion to the spaceship, so you'll measure L. Once again, according to the old theory, there's no difference. According to classical physics, L is the same as L naught. But according to Einstein's special relativity, so however, L is less by a factor of gamma. Okay, this is length contraction. So let's do a very quick example, and then this lecture is over. Let's do a quick example. So, same page, and the question is question 12, and it says, a spaceship that is 200 meters long as seen on board moves by the Earth, at 0.97 times the speed of light. What is its length? What is its length as measured by an earthbound observer? Okay, so this is exactly what we have described in the form of a diagram here. So the spaceship is 200 meters long as seen on board, as seen with somebody who is at rest with the spaceship. That's the proper length. This spaceship moves with a speed of of 0.97 times the speed of light. What is the length measured by an earthbound observer? That will be the contracted time. So these two are related, as I said, by gamma. So what we have to find now is gamma. What is gamma when V is 0.9c? Well, we go through the mechanics. So we shall divide both sides by c. So V over c is 0.97. And then we shall find, this implies that V squared over c squared, V squared over c squared will be 0.97 squared, which is 0.94090. 1 minus V squared over c squared is then 1 minus 0.94090, which gives us 5.9100 10 to the negative 2. So then we find the square root of both sides. So our gamma is then 1 over the square root of 1 minus V squared over c squared. So i.e., we shall now find the square root of this number here and then find its reciprocal. One over the square root of 5.9, what is it, 5.91 10 to the negative 2. Okay? We find the square root of both sides, and then we find the reciprocal. So, and that gives us 4.11345. So that means that's our gamma, right? So that means our length is 1 over this number here, 4.11345, times the original 200 meters. And this gives us 48.6 2098 meters, or 48.6 meters. And you can check to see that this is indeed correct, because the length that we ended up with is indeed contracted. It's shorter than the proper length. The proper length being the length that is measured when the spaceship is at rest with respect to whoever performed these measurements. This is the end of this lecture, and in the next lecture video we will look at the number of equations that Einstein had to rewrite to make sure that the laws of physics remained the same. The law of conservation of energy, for instance, the work kinetic energy theorem. We will rewrite another expression for the linear momentum of an object as a result of the fact that there is relative motion, and we shall write it in such a way that the law of conservation of linear momentum remains the same in all inertial frames of reference.